Greetings everyone. Today's topic is plant nutrition. This is the periodic table of the elements, and it shows the 103 elements that are known to mankind. Now, not all of these elements are needed for plant growth. So let's take a look and see what makes an element essential to plant growth. To be classified as essential, the element needs to meet the following requirements. Number one, the plant cannot complete its life cycle without it. Number two, the element's function in the plant cannot be replaced by another element. And number three, the element is directly involved in the plant's growth and development. So, if a particular element meets these three criteria, then it's considered to be an essential element for plant growth. In the following slides, we're going to take essential plant nutrients and we are going to put them into different groups. We'll start with non-mineral nutrients, but we'll also talk about primary macronutrients, we'll talk about secondary nutrients, and we'll talk about micronutrients as well. So what are non-mineral nutrients? They include carbon, hydrogen, and oxygen. And these nutrients are supplied to the plant in the water that it absorbs through its root system or by the carbon dioxide that it absorbs through open leaf stomata for photosynthesis. And all three are essential for plant growth. Another group of essential nutrients or elements is referred to as the primary macronutrients. So if we look at that word macronutrient, macro means large quantity. So these are nutrients that are used by the plant in very large quantities. There are three primary macronutrients, and those are nitrogen, phosphorus, and potassium. In parentheses at the end of each nutrient is the elemental symbol for that particular nutrient. N for nitrogen, P for phosphorus, K for potassium. There's another group of nutrients called secondary nutrients. And secondary nutrients are nutrients required by plants in smaller quantities. They're not required by plants in large quantities like the macronutrients were. They are essential for plant growth. It's just that the plant requires them in smaller quantities, and we call these secondary nutrients. The secondary nutrients include calcium, magnesium, and sulfur. Now there is one thing that everybody should be aware of. There is a school of thought that says that the secondary nutrients are really macronutrients, and some people will take calcium, magnesium, and sulfur and they will lump them together with the other macronutrients, nitrogen, phosphorus, and potassium. So just be aware of that. The last group of nutrients are referred to as micronutrients. If you look at the name, micro means small. These are nutrients that are required by plants in very, very small amounts. And there's a fairly extensive list of micronutrients that are all essential for plant growth, and they include iron, copper, zinc, manganese, boron, molybdenum, chlorine, and nickel. Let's add up all these categories of nutrients and see how many total nutrients are essential for plant growth. Let's go ahead and add up all these different categories of nutrients. Starting on the left-hand side, we had carbon, hydrogen, and oxygen, and we said those were non-mineral nutrients. And then we have three primary macronutrients: nitrogen, phosphorus, and potassium. We have three secondary nutrients: calcium, magnesium, and sulfur. And then we have the 8 micronutrients that we just went over. If you add up 3 plus 3 plus 3, that's 9, plus 8, so there's a total of 17 essential elements for plant growth. So the important thing to remember is that all 17 of these elements or nutrients are essential for plant growth. Plants just can't run their metabolism. They just don't work without these nutrients. It really doesn't matter whether the nutrient is required in a tiny, tiny, tiny amount or if it's required in a large amount. They're all essential for growth. This table is a nice reference that shows how the different elements are used by plants and in what concentrations they occur in plants. If you look at the first two rows, carbon and oxygen, you see that just those two elements or nutrients by themselves account for 90% of the nutrients found in plants. So if you were to take a plant and if you were to dry it in an oven and then grind it up and analyze all the different elements that that particular plant was made out of, we're saying that 90% of that plant would be made out of two things: carbon and oxygen. Hydrogen would account for 6% of the plant, nitrogen somewhere between 1 to 5%, potassium 0.5 to 1%, phosphorus 0.1 to 0.5%, and so on. And then skipping down to iron, which was a micronutrient, only 0.005 to 0.025% of the plant is actually iron. Liebig's barrel illustrates the law of minimum. What is this all about? Well, you're looking at a barrel, and imagine that this particular barrel is made up of planks. And let's pretend that there are 17 planks in this barrel. Each plank represents one of the 17 essential nutrients needed for plant growth. If the planks are at their longest possible length, then the barrel can hold 100% of water, or you can fill the barrel all the way up to the top. The water level in the barrel represents plant growth potential. When you look at this barrel, you can see that the plank for nitrogen is the shortest plank. This barrel cannot hold 100% of its water potential. We can only fill it to the level of the nitrogen plank. And at that point, if we add more water, it just starts to run out. So we'll never be able to fill this barrel up to the top. We'll never be able to reach 100% plant growth potential. That's because in this case, nitrogen is the nutrient that is most limiting plant growth. If you think back to the very first slide in this presentation, I showed you the periodic table of the elements, and each element represented in that table has its own particular symbol. As it turns out, mineral nutrients are not absorbed by plant roots in their elemental forms. So what do roots absorb? Plant roots absorb something called ions. Let me give you an example. A great example of what ions are can be found in a very, very common compound that everybody has in their house, and that's table salt, known by its chemical formula sodium chloride, NaCl. If I take a glass of water and then shake some salt into that water, what happens is that the salt immediately breaks down into its constituent ions. And those ions are the sodium ion, which has a positive charge, and the chloride ion, which has a negative charge. So sodium and chloride are examples of ions. Another example is found in ammonium nitrate. Ammonium nitrate is a very common source of nitrogen found in many different fertilizers. When ammonium nitrate is applied to the soil, it starts to dissolve in the soil water, and immediately it disassociates into its two constituent ions, which are the ammonium ion, NH4+, and the nitrate ion, NO3-. The ammonium ion and the nitrate ion represent forms of nitrogen that plant roots can absorb. When ions have a positive charge, we call them cations. When ions have a negative charge, we call those anions. As it turns out, the availability of nutrients, or these ions, is strongly affected by the soil pH. You can measure the pH of any soil, and what you see here is a graph that shows part of the pH scale. The full pH scale goes from 0 to 14, and we're looking at just a part of the scale between 4 and 10. And then inside of that box, you see different nutrients that are represented by different colored bands. The width of the band indicates the amount of that particular nutrient that is available at that pH. When the band is wide, that means that the nutrient is available in the maximum amount. As the band begins to narrow, that means that that nutrient is becoming less available as the soil pH changes. So let's look at an example. If you look at the very bottom of the box, you see the band for molybdenum. And we can see that at low pHs, or acidic pHs of 4, 4.5, 5, molybdenum is not very available to the roots of plants. When we get up to pH 6, 6.5, 7, which is considered a neutral pH, then molybdenum is available to the roots of plants to absorb. And molybdenum stays available to plants all the way up to pH 10. So the pH of the soil strongly affects the availability of these nutrient ions that plant roots can absorb. If the soil pH is out of whack and the plant can't absorb a particular nutrient that it needs for its growth and metabolism, then something called a nutrient deficiency can occur. In this picture, you're looking at a healthy leaf on the left and then a leaf on the right that is exhibiting symptoms of what's called iron chlorosis. Chlorosis means yellowing. If you look at the leaf tissue, you can see that it's a yellow color. The only part of the leaf that remains green are the veins. This represents an iron deficiency. If you find the bar for iron, you can see at high pHs, iron is not available to roots for absorption. So it's possible that this particular plant may have been growing in a situation where the soil pH was high, maybe 8 or 8.5 or higher, and iron was just not available, and as a result of this, the plant exhibits iron deficiency symptoms in its leaves. Fertilizer basics. One important aspect of a fertilizer is something called the fertilizer's analysis. In the picture you see an analysis that consists of three numbers, 16, 2, 3, on this bag of Screamin' Green fertilizer. Well, what do those numbers mean? The first number, 16, refers to the percentage of nitrogen found in that particular bag. The second number, 2, refers to the percent phosphate found in this bag. And the third number, which is 3, refers to the percent potash found in the bag. Phosphate can be converted into actual phosphorus, and potash can be converted into actual potassium. Why in the analysis are the terms phosphate and potash used rather than phosphorus and potassium? This goes back to the old way that fertilizer analyses were written back in the day when the source of phosphorus in a fertilizer was actually phosphate rock and the source of potassium in a fertilizer was actually potash. This archaic method of describing the analysis persists to this day. There are ways that we can convert percent phosphate to actual phosphorus and percent potash to actual potassium. Nitrogen, phosphorus, and potassium, remember, are 3 macronutrients that all plants need for growth. A complete fertilizer is a fertilizer that provides nitrogen, phosphorus, and potassium. If it has those 3 things in it, it's said to be complete. It doesn't matter whether the fertilizer provides any of the secondary nutrients like calcium, magnesium, and sulfur, or any of the 8 micronutrients that we already discussed. If the fertilizer provides a source of nitrogen, phosphorus, and potassium, we call that fertilizer complete. There are some fertilizers that are incomplete. In other words, they do not have all 3 of those primary nutrients, nitrogen, phosphorus, and potassium. Here are some examples. A 20-0-0 fertilizer would contain 20% nitrogen, 0% phosphate, and 0% potash. A 0-20-0 fertilizer would contain no nitrogen at all, 20% phosphate, and no potash. And in the third example, a 12-0-12 fertilizer would contain 12% nitrogen, 0% phosphate, and 12% potash by weight. If you want to know the percentages of the other nutrients that the fertilizer contains, you have to look at the fertilizer label. On this particular fertilizer label, the analysis has been circled in red. The analysis for this fertilizer is 12-4-8. If you look at the label, you can see that the total nitrogen is 12%, and that's broken down into 3 different forms of nitrogen. There's 2.7% ammoniacal nitrogen, 2% nitrate nitrogen, and 7.3% urea nitrogen. If you add those 3 numbers together, they add up to 12%. The second number in the analysis is 4, and that refers to the available phosphate that you find in the fertilizer. And the third number in the analysis, 8, refers to the amount of potash you find in the fertilizer. We can also see from this fertilizer label that it contains calcium, magnesium, sulfur, copper, iron, manganese, and zinc. But only the nitrogen, phosphate, and potash are included in what we call the fertilizer analysis. Types of fertilizer. There are some fertilizers that are water soluble, which means that these are powders that can be dissolved in water and they're applied to plants as a liquid solution. Other fertilizers are granular. These are applied as granules to the soil surface or to the surface of a potting medium if the plant is growing in a pot. Many granule fertilizers are slow-release fertilizers, which means that over the course of several months, they slowly release their nutrients into the soil or potting medium. Another way that we can classify fertilizers is on the basis of whether they're organic or inorganic. An organic fertilizer is a fertilizer that's derived from a source that is living or was alive at one time. So here's some examples. Bone meal and blood meal are both byproducts of slaughterhouses, and they are organic fertilizers along with manure, which is also another type of organic fertilizer. An inorganic fertilizer is a fertilizer that comes from a non-living source. In our industry, in the horticulture industry, we primarily use inorganic, granular, and water-soluble fertilizers. We generally don't use organic fertilizers because it's hard to know their rate of release. Well, that was a quick look at plant nutrition. Thanks for watching.